Um, Give me a moment. Okay, welcome to my class on set theory. Welcome. As you come in, please drop a like on the video, endeavor to turn on your notification and subscribe to the channel if you haven't subscribed. Let's begin today's class. Today we shall be discussing set theory, our continuation on set theory. We shall be discussing several things about set theory we did not discuss in yesterday's class. So that's what we shall be doing in today's class. Okay. So please, could you do me a favor? Kindly let me know if all is set and all is good about the class. Kindly let me know in the comment section. Please let me know. Please let me know. Thank you very much. I welcome all your comments in the comment section. Please kindly let me know. Okay? If you can hear me clearly, kindly let me know in the chat before we begin. And if you can see what I'm writing clearly, please also let me know in the comment section. Please do that quickly for me. I really appreciate. Please let me know. Okay? So, in the absence of any comments, let us begin. So, in today's class, guys, what we will be discussing will be our continuation of set theory. So, I'm going to give us a quick recap on what we did yesterday. So, what did we do yesterday, just in case this is your first time of joining this class? What did we do in yesterday's class? In yesterday's class, what we discussed were the following. We discussed the definition of a set. So, set definition. We discussed the definition of a set. So, we answered the question, what is a set? This was answered in yesterday's class. Okay? In yesterday's class also, we looked at set description. Set description, and we also discussed set description. So those are the two discussions we had. So let's start with reminding ourselves. Okay? So first thing, just in case you did not attend yesterday's class, what did we define a set to be? A set is a collection. We said a set is a collection of well-defined objects. We said a set is a collection of well-defined objects. That was our definition of a set. And in that same class, we had another discussion. There is another definition that looks like the definition of a set, but it's not correct. So we said this definition that says a set is a well-defined collection of objects. We said that this definition that says a set is a well-defined collection of objects, we said in yesterday's class, is wrong. So out of the two definitions, guys, in yesterday's class, we said this one is correct and we said this one is wrong. Okay? So that is just a reminder. Now, after discussing this, I gave examples as to why, and I gave explanations as to why the first definition is the correct definition of a set, and the second one is not a correct definition of a set. Please, if you are just joining this class, if it is clear enough, if you can hear me clearly, please drop a comment. I want to know that I'm actually talking to people. I want to know that what I'm saying is clear and loud enough. So please let me know in the comment section. So now, after we said this, we now went on to set description. And under set description, in yesterday's class, I told all the students that were in attendance that there are two categories of describing a set. Two categories to the techniques for describing a set. Thank you very much, Victor Bala. I can see you. Thank you very much. So, I said in yesterday's class that describing a set can be done in two ways. So one way to describe a set is using what we call theoretical way or theoretical technique. Theoretical technique. So sets can be described or could be described using theoretical techniques. Okay, so we said that yesterday. And the second way or the second category of techniques for describing a set is what we call diagrammatical technique. Now you will find, for details of this particular lecture of yesterday, you can go back to the video in my channel. So when I mentioned this in yesterday's class, I went further to say that there are three theoretical techniques for describing a set. So even though we can classify set description into two categories, namely theoretical techniques and diagrammatic techniques, the theoretical techniques can be classified into three categories. The first one is the method of listing. The method of listing, we call it listing technique. So listing technique is a theoretical technique. Thank you, Victor Bala. So listing technique is a theoretical technique for describing a set. The second one we described yesterday is set properties. Thank you very much. It shows that somebody had followed up this class. And the third one for describing a set theoretically, we said, is the method of set theoretic notation. Thank you, set theoretic notation. And I told us in yesterday's class that set theoretic notation could also be called set builder notation. So those were the three theoretical techniques we discussed in yesterday's class. Now, coming to the diagrammatic technique, we said that there is one diagrammatic technique called the Venn diagram. So the Venn diagram is a diagrammatic technique for presenting or describing sets. Thank you very much. So I'm grateful that somebody follows. Now, these were the things we discussed in yesterday's class. In today's class, what will be the focus, therefore? In today's class, I want us to look at two major items. So what are we going to be discussing in today's class? Number one, the focus for today's class will be on definitions and remarks in set theory. Definitions and remarks in set theory. That is the first thing we are going to look at in today's class. The second thing we are going to look at in today's class will be set operations. So we will continue wherever we stop on that. So please take note, the focus for today's class, will be on these two, this and this. The first will be definitions and remarks in set theory. The second will be set operations. So quickly, without much waste of time, guys, let us start the next thing. This class would stop by 10 o'clock. So let us start with definitions. The first subtopic, definitions and remarks. Definitions and remarks in set theory. Okay? So that is the first thing we should start with. Now, number one, let's start with remarks. Okay? So I'm going to start with remarks. So let's call this remark number one. So the first remark I want to make in today's class, please take note of everything I say, is that sets, although I said this yesterday, but please take note, sets are generally represented with capital or uppercase letters. That is the first remark I'm going to make. Remark number two. So what that first remark means is that in set theory, in studying set theory, please take note, we don't use small letters to represent sets. We use capital letters. Now, not in every case will you use capital letters. it can be specified. A set can be specified aside using capital letters. It can be specified by any other thing, but conventionally we use capital letters. But if you want to use something different to specify a set, then you have to tell us. You have to let whoever is reading your write-up know in advance that this particular symbol or letter will be used to represent a set. Otherwise, sets are generally represented with capital letters. Number 2, elements or objects. Objects in a set are called elements. We said this when ending the class yesterday. Objects in a set are called elements or members or components. Okay, so objects in a set are called 1, elements. If you don't want to call them elements, you could use the word members. If you don't want to call them members, you could use the word components. Okay, so please take note of that. So going to number 3, remark number 3, everybody. So remark number 3 is that we had said this yesterday, but I'm going to emphasize them as a remark. Okay, we had said this yesterday, I'm going to emphasize them as a remark. Now please take note, this symbol, if I have an element A and I want to tell you that the element A is a member of a set, capital A. For you to write this or describe this in set theory, we have a symbol for doing that. The symbol, instead of writing this long sentence, the element A, small a, is a member of a set A. You could simply use this symbol in between, the symbol in between. So this symbol here, this symbol I have just written is called a membership symbol. Okay, the symbol is called a membership symbol. So you use this symbol to tell us that an element such as this small letter a or lowercase a is a member or an element of or is contained in A. Take note, this statement here, once I write like this, I can now interpret it as follows. I could say the element A is a member of A, the set A. If I don't want to use that statement, I could say the element A is an element of the set A. If I don't want to say that, I could use the language, the element A is contained in the set A. So anyhow you want to describe it, you will be referring to the same thing. But please take note that this symbol is called the membership symbol. Now, what if I write A is not a member of the set A, of a set A? What if I want to put this in symbol? I could also do this. A is not a member of A means all you have to do is to put a cross over this symbol. So once you put a cross, a stroke over this symbol, that is the membership symbol, it gives us a symbol we call a non-membership symbol. So it becomes a non-membership symbol, okay? So A is not a member of A can be written as A slash over the symbol of membership, A. A is a member of a set A can be written as A, the membership symbol, the set A. So please take note of that. Now, the next remark, please, we are looking at remarks and definitions. So the next remark I want to make is remark number 4. I hope you are following. Remark number 4. Please, if you are following, please let me know by indicating in the comment section. So remark number 4, set elements. Thank you. Set elements are always enclosed. Set elements are always enclosed in what we call a curly brace. A curly brace, okay? So if an element is found in a set, you can actually put that element or the elements found in a set in what is called a curly brace. In yesterday's class, I had used curly braces in my example. So if, for instance, I have orange, I have mango, and I have pineapple as three fruits in a set we call the set of fruits. Now note that in putting these elements in that set, I have used a curly brace. Please, a curly brace is something of this nature. It is not this. This is a square bracket. It is not this. It is this. So this is a curly brace. For set theory and in set theory, we use curly braces to contain the elements of a set. So please take note of that. Now, let's now move over to definitions. Let's move over to definitions. Okay? Okay, there's one more remark I would love to make. So, remark number 5. Now, for remark number 5, just before we proceed, please take note. Set elements are unique and distinct. I'm going to explain what that means. Set elements are unique and distinct. What that means is that if, for instance, I have a set A that contains 2, 3, 3, 5, and I have another set B that contains 2, 3, and 5. Please take note. These two sets are the same. The two sets are the same. If a set contains 2, 3, 3, and 5, and another set contains 2, 3, and 5, they are the same. It means that the elements in a set, in set theory or in set, we don't accommodate repetition. These two elements, 3 and 3, they count as 1. Okay? No matter the number of times an element finds itself in a set, it is counted once. So set elements are unique and distinct. I repeat, set elements are unique and distinct implies that the number of times a particular element reoccurs in a set does not matter. Even if a particular element in a set repeats itself 50 times, it will be counted as 1. So please take note of that. So in that sense, these two sets are the same, simply because all we see in set theory as it concerns these two sets is 2, 3, 5, no matter the fact that 3 occurs 2 times. Another thing you must take note is this. Order does not matter in a set. So if I have a set 2, 3, 5 as A, and I have the set B, 5, 3, 2, both of them are the same set. So order does not matter. So even if you put the first element followed by the second and put the third as 5, it is still the same thing as 5, 3, 2. So order does not matter. Repetition does not matter in a set. Thank you very much. So those are 5 remarks we have taken. Let us now go to definitions. So for definitions, just in case you are just joining us, you could smash a like on the video and drag the video backwards by taking that red line. You can drag it backwards to follow what we've done so far, or watch the video after the class. What we are discussing, just in case you are just joining, our focus for today's class is definitions and remarks in set theory and set operations. So we have started with looking at definitions and remarks in set theory. I have just presented 5 remarks. You can go over the video again to watch the remarks. They are very important in your knowledge or learning of set theory. Now that we've taken the 5 remarks, let us now go to definitions in set theory. So definitions. Let's go over to definitions. Okay? So the first thing I want to say, the first definition, let's call it definition number 1. Definition number 1. Okay? So what are we doing in definition number 1? In definition number 1, I want to talk about what we call finite sets. Okay? So this definition is on finite sets. Okay? So what is a finite set? A finite set is a set whose elements are countable and exhaustible. I repeat, a finite set is a set whose elements are countable and exhaustible. What that means is that when a set is said to be finite, it means that the elements in that set, you can actually count them, okay? They can be counted. And not only can they be counted, you can also finish the counting of the elements in what is called a finite set. I repeat, a finite set is a set whose elements can be counted. In other words, they are countable and whose elements are exhaustible, meaning that when a set is finite, you can count the elements and can also finish the counting. Good. That being the case, let us now take examples of finite sets. Examples. So a set like this, A, that contains A, B, C, and D is a finite set. Why? I can count the elements in the set A, B, C, D. There are 4 elements, and I can finish the counting. The counting starts at A and ends at D. A set also like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is also a finite set. Why? I can count the elements in the set and I can finish the counting. It starts from 1 and ends at 10. Now, it gets very interesting, guys. A set is finite even when it is large. Now, in notation, in set theory, please take note. When a set is large, does not mean, because the set is large, does not mean it is infinite. A set can be large, but yet finite. For us to express a large set that is finite, what we do in set theory is to use what we call ellipses. Now, let's assume that I want to count the elements of a set that starts from A and ends at Z. When you want to count a set that is large, a finite set that is large, in the case of this instance, we put 3 dots. These 3 dots are called ellipses. Conventionally, these 3 dots, they go as one. They are called ellipses put together, okay? So these 3 dots will follow. If you want to describe a large finite set, you list the first 3 elements, A, B, C, put 3 dots, which is ellipses, and put the last element in that set. So this is the set of all English alphabets. It starts with A, is followed by B, followed by C, and since the set is large, I will put ellipses and then end it with Z. Now, if I want to write a finite set that begins from 1, followed by 2, followed by 3, and proceeds to 100, all I will do is to put the last element after 3 dots, the ellipses, okay? So a set can be finite and yet be large. Please don't confuse a large set as being an infinite set. Once again, for a set to be called finite, please take note, it means that that set has elements that are countable and exhaustible. Countable in the sense that you can actually count them, exhaustible in the sense that you can finish the counting. Looking at these examples, you will see clearly what a finite set is. Now, let us go to definition number 2. Definition 2. Definition 2 talks about infinite sets. Infinite sets. Okay? So, when is a set infinite? Now, a set is infinite if a set is infinite if its elements are countable but inexhaustible. Now, people often think that when a set is infinite means that the set elements cannot be counted. No, you can actually count the elements of an infinite set, but the problem with an infinite set, what makes it infinite is the fact that you cannot finish the counting. Please take note, a set is infinite if the elements of the set can be counted, but the counting cannot be exhausted. So please take note, for that reason, a set like this, A equals A, B, C, if a set is infinite, we list the first 3 elements and put ellipses without an ending element. So this set, compared to the other one, is infinite because we only know the first 3 letters, but we don't know where it ends. So I could also have a set like this, B, that contains 1, 2, 3, and we don't know where it ends. So looking at it clearly, a set is infinite if its elements are countable but inexhaustible. So you can keep counting the elements of the set, but you will never know where it ends. For that reason, we use ellipses after the first 3 elements to show that the counting continues to an unknown destination. So a good example of infinite sets are the numbers and the number systems we have in mathematics. When we get into numbers, we will get or revisit that matter. So number systems like the integer number systems are infinite. The natural number system is an infinite set. The real number system is an infinite set as well as an uncountable set. Now, let us now move on to the idea of countable and uncountable sets. People often confuse finite sets and infinite sets to be the same as countable and uncountable. So definition, let's go over to definition 3. Okay, let's go over to definition 3. So for definition 3, please take note. We are looking at countable sets. We are looking at countable sets. Okay, so when is a set countable? A set is countable if the elements of the set, a set is countable if the elements of the set can be assigned numbers that show order. Okay, so if the elements of a set can be assigned numbers that show order in that set, or that set is countable. For instance, if you have mango, if you have pineapple, you can hear them now. Excuse me, I took a quick break. Sorry. Now, I'm talking about countable sets. Okay, so definition 3. I'm countable if the elements of the set can be assigned numbers that show order or listing of that set. Please take note. A set is countable if the elements of the set can be assigned numbers that show order or listing. Now, if I have mango, pineapple, apple, orange as members of a set, this set is clearly finite, and at the same time, it is countable. Why it is finite is different from the reason why it is countable. Please take note. It is finite because the elements of this set can be counted and you can finish the counting. The reason why it is countable is because to mango, I can assign the number 1. To pineapple, I can assign the number 2. To apple, I can assign the number 3. To orange, I can assign numbers uniquely to these elements of the set in order to count them. Okay, so the reason why they are countable is different from the reason. So this particular set to which you can assign its elements numbers that show order in the set can be called a countable set. Okay, however, definition 4. Now moving over to definition 4, uncountable. Students often confuse uncountable sets to be the same as infinite sets. Now, please take note. A set is uncountable if the elements of the set, cannot be assigned numbers that show order or listing of its elements. Now, let's take a look at this. If I tell you to if I tell you to describe this set, a set that contains elements between 0 and 1. Okay, let's assume that the set A is the set of all x such that x is a real number and x lies between 0 and 1. So please take note. If I give you a set like this, a set that describes every real number that lies between 0 and 1, you won't be able to describe this set because to the elements of this set, you cannot assign a unique number that shows the order of elements in the set. To start with, let me break this down. If you are considering real numbers as x that lie between 0 and 1, the question is, what real number follows immediately after 0? You may end up answering that question by saying that the next real number that follows immediately after 0 is 0.1. But you'll be wrong, because the next real number that follows immediately after 0, in between 0 and 0.1, lies infinite numbers that are real. So you can't tell exactly what number follows immediately after 0. Okay? So please take note, a set like this is uncountable because we cannot assign to the elements in that set a unique number or unique numbers that show order. Now, please let us now move on to the next definition. So the next definition is definition 5. Let's move over to definition 5. Definition number 5. Please, if you are still watching and this video is very clear, that is, you can see what I'm writing clearly, please indicate in the comment section. Please let me know. I want to be sure that at all points and at all times in the course of this class, you can see what I'm writing clearly and you can hear me clearly. I want to be sure of that. It is very important because with that, thank you very much, Victor Bala. You are really making me happy in this live class because you are following everything and you are making me know the progress made. Thank you very much. So let us go to definition number 5. So for definition number 5, I want to define what we call a null set. What is called a null set? Okay, so let us define what is called a null set. Guys, what is a null set? A null set is also called an empty set. I repeat, a null set is also called an empty set, but that does not define it. You can put the definition clearly by saying a null set is a set that contains no element or member. So if a set contains no element at all, or it contains no member at all, that set is called a null set. If you don't want to call it a null set, you will call it an empty set. So empty set or null set refers to one and the same thing. They are sets that contain no element. Now, still under this definition, please take note. A null set can be denoted either by the symbol this or the symbol this, an open brace. Okay, so you can use an empty set, or you can use this or this to denote a null set. Okay, guys, please, I will continue this class tomorrow morning. I will continue this class by the grace of God tomorrow morning. I would want to stop here at this point because I'm being signaled. I'm getting signals of technical errors being experienced. So sorry for that. We are going to continue this class from this point tomorrow, and I'm going to schedule the class. If I don't have the class tomorrow morning, I'm going to have the class later in the evening, but I'm going to let you know in any case when the class will hold. So let us stop here because I'm being signaled I'm having signals from my phone as to technical errors. Thank you very much for watching this video. Please subscribe to the channel if you haven't subscribed, and share our videos, and endeavor to bring your colleagues here Make them know that a class like this is holding at different points in time. Thank you very much and good night. Bala, I'm very grateful. Thank you very much.